Alright, so I can talk to you about tidal disruption events and how STROBE-X can actually give some information about them. But before I go into this, I will give obviously some background to give the context of why we want to study tidal disruption events. So if you go to my second slide, so we know black holes with masses greater than approximately 10 to the 5 solar masses reside at the heart of most galaxies, and the most direct evidence for the existence of these massive objects comes from the detection of AGN activity. However, we know that models of black hole evolution suggest that there exists a large number of quiescent black holes in which gas accretion occurs at a significantly slower rate than those seen in AGN, making it difficult to be able to study these objects using similar techniques that are used for AGN. And so if you go to my third slide, one way in which we can prove the properties or existence of a black hole at the center of a quiescent galaxy is by using tidal disruption events, which results from a star being ripped apart by the strong tidal forces of the black hole. And so when this disruption occurs, half of the stellar debris will escape the black hole, while the other half will be confined to a bound orbit, which will circularize and form an accretion disk, which will eventually be accreted onto the black hole, producing a luminous, short-lived accretion-powered flare. And so if you go to slide 4, one thing you find is that when these type of events occur, that they usually peak within the optical energy or the soft X-ray energy bands as seen in the top, in the top figure. And so it's expected that when you detect these, that the luminosity of these events will decay following a power wall, which is usually set by the time scale in which the stellar debris eventually returns to pericenter. And so this time scale usually is assumed to follow a T-5 power law. However, exactly how this index changes or how this what you measure depends heavily on the evolution and its physics within the accretion stream associated with the event. And so since these sources emit at various wavelengths, mostly time-domain surveys have dramatically helped us in detecting and characterizing the properties of these events. However, realistically, searching for TDEs in X-rays has actually been quite fruitful. With now the number of TDE candidates that we detect in X-rays outnumber those we detect in UV or optical. And this has been quite important because of SWIFT, particularly, but obviously XMM and SAM have been quite, and ROSAT as well, have been quite important trying to really detect these and really detect and follow up potential TDEs and X-rays. But I think actually STROBE-X would be is actually really ideal in all its aspects, and that it will be an integral part in detecting and characterizing and following the X-ray emission from these events, which will complement upcoming instruments associated with X-rays and other wavelengths. And so, if you go to my next slide, one of the questions that is usually asked when I talk about TDEs is why would you want to be interested in looking at the X-rays from these events? And so the advantage of X-rays instead of over optical UV wavelengths is that one is actually directly probing the accretion stream associated with the accretion activity associated with these events, while simultaneously minimizing the potential confusion that can occur between TDEs and other transient sources that you find in optical wavelengths. In addition, we can actually detect the formation and evolution of a jet, which is powered by the sudden accretion episode, which you can't really do in the other wavelengths, except maybe radio. But I think more importantly is that if one is able to look at like years of data associated with these events, if you detect either recurring or incoherent decaying X-ray emissions from a transient, you can quickly rule out that this is going to be a TDE because it's more indicative of an AGN. And so really this kind of gives a very broad picture of how to kind of characterize is it a TDE or not, as well as giving the real information about the physics associated and properties associated with these sources. And so if you go to the next slide, or the X-ray TDE demographic slide, one thing we find is that at the moment, at the moment, this is our current idea of what we know as TDEs and X-rays at least. And so in the literature, signature, there was over 70 transient sources that had been suggested to arrive from the tidal disruption of a star. But I can show that you can actually, one, you kind of properly characterize the X-ray emission from this. Mostly you find that not all of these, we don't have enough data usually to try to find it, to characterize the TD or in the center of a galaxy as an extra TD. And so these events here are the main ones which have enough data and information to be able to say, yes, this is more likely to be a TD rather than just some random flare, or we just don't have information to be able to constrain it. The one thing you find here is that on this plot that you can see is that there's kind of two types of classes of X-ray emitting TDs. At the top you find jetted events, and so these are the ones that usually exhibit a jet, which is indicative of super Eddington accretion occurring in these events, while the large majority of them, which you see in the bottom part of this figure, are actually sub-Eddington in nature and don't tend to produce a jet here. If you go to the next slide, apart from these X-ray defined classes, there's another class which I won't really talk about, but what I call veiled X-ray TDEs. And so these ones are predominantly seen in optical or UV wavelengths, but you don't see they don't show any evidence with our current observations of X-ray emission here. But I won't really talk about these, but I think STROBE-X could still pose some questions about actually do you see X-ray emission from these. I just wanted to give you an overview of where we currently know, what we know about X-rays, what we know about the X-ray emission of TVs here anyway. And so if you go to my slide 8, these are some of the questions that I think that STROBE-X can answer or try to answer before tidal disruption events. And so, and some of these are some of the major questions currently in the field that we are currently trying to answer with, but I think STROBE-X would really be able to pinpoint this quite well. And so these are kind of, what are the rates of TDs, what are the rates of TDs, in particular those seen with a jet? What are the rise times, so how quickly does a TD flare or begin that we detect it compared to pre-flare upper limits? How does this X-ray emission evolve with time? Because, that's currently what's really making one of the biggest issues in TDs is not being able to observe them sufficiently enough to see how it evolves. And of course, what is the geometry of the accretion flow associated with this, and what are the properties of the black holes themselves? And so if you go into the next slide, I tried to give the context of this. So, why do we want to consider the rates of TDs? Well, it's really important to understand how rare these events are, because this obviously has important consequences for our observational searches and also for our theoretical understanding of how these events are produced. At the moment, theoretically, it's expected that for a black hole mass of around 10 to the 7, we expect maybe one tidal disruption event per 10,000 galaxies. And so the consequence, usually time domain surveys covering a wide range of view, which are mostly observed in optical, have been important in trying to detect and characterize these events. However, I had pointed out before that a large fraction of the luminosity arising from a TD should fall in the X-ray energy band. And so, searching for TDs in a more systematic way, I think is of great importance. And so, STROBE-X with its with its wide field monitor should be able to really help us constrain this information and kind of search for TDs in a kind of more systematic way than what can be done at the moment because we don't have that ability. And in particular, I think this is important because it will put important constraints on the jetted TDs. And so jetted TDs, TDs exhibiting a jet were not expected originally. We usually expected that they would not produce a jet. And then when suddenly Swiss detected 3 of them, it was kind of a bit of a surprise. And so people have tried observationally to try to put a constraint on what the rate of these events are using MAXI, but the uncertainty in this is quite large. It's either a really small percent of all TDs produce a jet or a lot of them produce a jet. And so, if we can if we can take advantage of STROBE-X wide field monitor to really kind of survey a large fraction of the sky above 2 keV, we can be able to place constraints, observational constraints on, which ones produce the jet, what's special about do they happen to be at a particular redshift compared to other ones, because currently the jetted events are only found at redshifts of about 0.8 compared to the rest of the population, which is mostly found at 0.2. And so this is kind of really important. And the fact that the STROBE-X will be able to detect some of the brightest events because of the this will actually help us be able to really characterize the differences in the properties of jetted TDEs using either both STROBE-X itself, using its other instruments on board, or using other space-based or ground-based instruments that are available at that time. And if you go to the next slide, apart from being able to, constrain the sources from this, in particular, it's very important for us to, it's also the wide field monitor actually will give us really important advantages in trying to understand how quickly the accretion processes occur in a TDE, especially when they emit in either optical or X-ray wavelengths. And the reason why I say this is that currently we are not very good at being able to detect when TDEs actually rise up to peak or when we detect them, or we haven't detected kind of that dramatic increase in energy, in luminosity that we expect to come from a TDE. And so most of the time, we've got reasonable constraints in optical wavelengths, but for X-rays, it's not clear how quickly you get to peak from tidal disruption events. And so, usually we only have upper limits that are only many years beforehand. But with STROBE-X being able to observe kind of a large fraction of the sky and kind of accurately pinpoint observation or transient sources quite well, this could really help with being able to say if something is a very prompt event, so you suddenly increase in luminosity or whether it's kind of a slow increase in luminosity from this. And so understanding that has actually important implications for understanding the underlying accretion processes. And so in the top figure on this slide, this paper here actually showed that knowing when the TDE peaks the changing when the TDE peaks in your modeling can actually dramatically change what one expects the potential accretion process to be within uncertainties. And so you can really pinpointing that down can really help us understand the underlying processes that really constrain the light curve decay we observe. But also a lot of theoretical work in trying to understand, the TDEs dramatically increase in luminosity or is there a slow increase. And there is evidence, or there has been a suggestion that maybe there's two types of classes of TDEs. So ones that are associated with this rapid increase or this prompt emission, or one that is slow rise to peak. And so currently all of our TDEs that we detect now are classified as these prompt events. And this is mostly because our observing strategies that we have are really biased towards detecting prompt flares, right? You don't see anything and then suddenly you see something here, but STROBE-X should be able to really, with its monitoring ability, and constraints on kind of a large fraction of sky, should be able to help us really detect or determine whether you actually see if everything is always prompt, so you suddenly see nothing, you have nothing and then suddenly it increases, or if you suddenly see, or you slowly see an increase in X-ray luminosity that is indicative of some increasing accretion process from here. And so that's a big question that hasn't really been answered with current observations, because of the fact that we just not made our observatories are just not made for this type of study. And so if you go to the next slide, apart from trying to work out, when do they turn on? When do TDs turn on? Another important thing is like, well, how do they evolve in X-rays? And so currently, only a handful of TDs have a well-defined X-ray light curve. And so the ones that are plotted here are actually the two main events in which we have we have reasonable amount of data. So this is the Sassen 14I and Swift J1644, where one is a non-jetted TD and the other one is a jetted TD. And so most of the time, with current observations, we either just have really short exposures, and so we might be unlucky and miss most of the decay, or just the exposure is just not long enough to be able to put a constraint on the X-ray emission. And so, the STROBE-X, which should be able to detect really nearby and bright transient sources from these things, it should be able to monitor them really well, and really for us to help constrain how, what variability we observe in the X-ray light curves, how it decays with time, and in multiple wavelengths, which is a real important part of understanding TDs, which is currently really missing. I think, especially above maybe like 5 keV, most sources are not really observed at all above that from the net. And so being able to have this really large X-ray energy band, looking at these sources would really help constrain understanding like the spectral energy distributions of these events. Where do they mostly put energy in here from this? And really understanding spectroscopically how they evolve with time, which is not really well constrained at this moment, except for only two events out of a possible maybe 70 of them. And so I tried to do a quick simulation of what we would expect or how quickly one would be able to observe to get a very similar result to what we observed with like Swift J1644, where we had a lot of observational data. And within 1 kilosecond of STROBE-X, we get a really, really nice spectrum straight away without any problems. And even at its later times where we were observed, where most of these observations with Swift were observed with for many, many kiloseconds, like tens to hundreds of kiloseconds, STROBE-X should be able to actually just detect or like be able to get a spectrum from this pretty quickly, which would be really quite exciting. And even though it's CCD quality, I don't think that's an issue at this moment for this, because obviously you can complement STROBE-X with a scanner and then other observations. So if you also go to the next slide, and apart from being able to see how it evolves, one of the really important things that we want to understand is how does the TD accrete, right? What is the structure of the disk around that is produced in a tidal disruption event, and how does this process occur? And so I actually, STROBE-X is mostly made for studying, the impressive area associated with STROBE-X is ideal for studying reverberations, for AGN, but exactly that type of study can be applied to TDs. And I think this is a really nice window that STROBE-X can kind of prove itself or really shine for tidal disruption events. And so currently, there's only an example of one TD, which is a jetted event, in which we've been able to detect, done reverberation mapping of redshifted ion K alpha photons, which have been reflected off the inner accretion flow of this TDE. And so this was actually done by Erin Kara, who is also a part of the STROBE-X scientific committee, or who's also a part of STROBE-X. And so, from this she had I think it was a 25 kilosecond XMM observation, and they do detect at the very start of the event. So this is at the very peak of this, the tidal disruption event, this very kind of highly redshifted ion line, which has been redshifted to 8 keV, which is indicative of that there must be very fast fluid moving at about 15% of the speed of light. And so this was only done for one part of the observation or part of the TDE, but it would be really nice if we could see how that changes with time or how it decays, and really kind of trace out the velocity distribution of of this accretion flow as the event kind of evolves with time. And so STROBE-X can really, I think, do this because the fact it can collect so many photons in a reasonable observation exposure time that really would make this instrument amazing for tidal disruption events. And in fact, also, it would also help, like, if we can do this, if we could do this type of mapping for all tidal disruption events, we can really work out, well, maybe the swift event that we observe, whether that's just a special case or whether we see this type of interaction with all type of TDEs or not, and really compare them to what you see also in AGN, which is currently not as well done. The hardest part of tidal disruption event studies at the moment is that these AGN produce flare-like emission and properties very similar to other TDEs. So really trying to extract that information and kind of separate these two classes of flaring information would be really important. And I think STROBE-X could start really doing this for that. And if you go to my next slide, which is the last slide before I kind of finish it up, because I know I'm already over my 15 minutes. The next thing is that, much like AGN studies using reverberation mapping and various things, that STROBE-X can really kind of help us constrain the black hole masses and this black hole spin associated with these events. These are really big questions that we have in our field at the moment, is what what we're really trying to do is trying to constrain the black hole masses of these events to give an insight into how black holes evolve, and also what properties of their host galaxies would really promote the production of tidal disruption events. And so for example, most TDEs we detect now seem to have, or are consistent with black hole masses between 10 to the 5 and 10 to the 7 solar masses, but there's been evidence, or possible evidence, that maybe black holes greater than 10 to the 8 can actually also produce tidal disruption events. And so usually this is not allowed, or it's not really expected, because the tidal radius associated with the black hole is usually found within the sphere of influence. And so the only time you can disrupt and so usually expect that the star would just be swallowed completely. But if the black hole has a really high spin, it can actually disrupt something that could not otherwise be disrupted. And so we have one event so far that could possibly do this, which is called Assassin 15LH. And so I think that, which is a very bright transient, and so because STROBE-X is really good at detecting bright transients from this, STROBE-X could probably actually start constraining, the rates of these really unique events, these ones from very high mass black holes, as well as, of course, as black holes of the whole the whole population, by doing these various things that you apply to AGN to these tidal disruption events as well. And so that would kind of be a really nice thing, really another way to really kind of probe the quiescent galaxies that we observe in our universe that would be important for us to understand here. And so my last slide, I know I only had 15 minutes and I kind of rushed through that really quickly, but I listed a lot of other questions that I thought that STROBE-X could probably kind of think about as well. And so, that ranges from how do we correlate this with other wavelengths, understanding the relationships between different thermal emission and non-thermal in these events, as well as, what other information can we pull out, can we constrain like an X-ray luminosity function of tidal disruption events with these things, or can we somehow survey a large number of galaxies using this to really constrain, do we only see TDEs in a particular type of galaxy, which is kind of suggested by current results, or are they also found in other galaxies from this? And so, STROBE-X can really, I think, give a nice overview of the X-ray emission, which would complement a lot of other instruments that's currently aiming to observe these. And so I think I'll finish there. From there, I'm sorry that I rushed through that very quickly.